All right, welcome. Getting stuck into your GCSE chemistry revision? Well, you are in exactly the right place. In this quick explainer, we're going to get to grips with one of the most fundamental topics out there: how the bonding and structure of a substance completely decide what it's like. Let's just jump right in.
Okay, let's kick things off with a bit of a puzzle. You've got regular table salt, right? To get that stuff to melt, you need to crank the heat to over 800 degrees Celsius. But then you've got ice, just frozen water, and that melts in your hand. So what gives? Why is there such a massive difference? The answer to that is the key to absolutely smashing this part of your exam.
And here's the secret. It all comes down to this. Every single physical property of a substance, and I mean everything, is decided by just two things. One, the type of chemical bonds holding it together, and two, its physical structure, so how all its atoms are arranged. Once you get this, honestly, the rest just clicks into place.
Okay, so first up, let's tackle our ionic compounds. Just think back to that salt example. We're now entering the world of giant, super strong structures. So what we've got here is what's called a giant ionic lattice. Now the keywords there are giant and lattice. This isn't just a few ions chilling out together. No, this is a huge, perfectly organized 3D crystal. It's kind of like a massive, perfectly built wall of Legos, with positive and negative ions repeating over and over again.
So what's the glue holding all this together? Well, it's these super strong electrostatic forces of attraction. Think of it like the pull between the opposite ends of a magnet. You've got your positive metal ions and your negative nonmetal ions pulling on each other. And the crucial bit is, these forces are yanking in all directions, which locks everything into this incredibly strong, rigid structure.
So how does this actually explain its properties? Well, to melt an ionic compound, you have to break all of those strong forces holding the lattice together. And that takes a huge amount of energy. That's why the melting point is so high. And what about conductivity? Well, when it's a solid, those ions are totally locked in place. They can't move, so no electricity can flow. But the moment you melt it or dissolve it, those ions are free to move around and carry a charge. And that, right there, is a classic exam question. So remember that one.
All right, now let's flip the script completely and look at our second type, simple molecules. This is the complete opposite of what we've just seen. This is the world of things like water, ice, and carbon dioxide.
So, totally different from that giant lattice, these are just small, individual molecules, little separate packages like H2O or CO2. Instead of that solid brick wall, think of it more like a bag full of marbles. There's no giant connected network here.
Okay, and this is probably the most important thing you need to get your head around. The bonds inside the molecule, like between the hydrogen and oxygen in a water molecule, they are super, super strong covalent bonds. But, and this is the big but, the forces of attraction between one water molecule and the one next to it are really, really weak. We call these intermolecular forces.
And that one little fact explains everything about them. To melt or boil something like this, you're not breaking those strong bonds inside the molecules. Nope, you only need a tiny bit of energy to overcome the weak forces between them and nudge them apart. That's why their melting and boiling points are so low. And since the molecules have no overall charge and there are no free electrons, they just don't conduct electricity at all.
In this chart, it just screams that point right at you. Look at the energy needed. For simple molecules, it's tiny. You're just pushing weakly held molecules apart. For the giant structures, you're trying to break countless powerful bonds. It's not even close, is it? The difference is just massive.
Okay, we're on the home stretch. Let's look at the other two giants you need to know: giant covalent structures and, of course, metals. So, let's put them head to head. With giant covalent structures like diamond or silica, every single atom is locked to its neighbors by strong covalent bonds. It's basically one single huge molecule. Then you have metals. Here, you've got this lattice of positive ions just sitting in what we call a sea of delocalized electrons. Basically, these electrons don't belong to any one atom. They're just free to whiz around the whole structure. So with these giant covalent guys, you have to break actual strong covalent bonds to melt them, which takes a huge amount of energy. That's why their melting points are just through the roof. I mean, think diamond. And since they don't have any free-moving charges, they don't conduct electricity, with graphite being the famous exception you need to know about. Metals? Yep. They also have high melting points because of that strong attraction between the positive ions and that sea of electrons. But the real game changer, the special trick for metals, is that sea of electrons. Because they're free to move, they can flow through the metal, carrying an electrical charge. It's also why they're great at conducting heat.
Right. We've done all 4 types. Time to bring it all home. Seriously, this next slide is pretty much your golden ticket for revision on this topic.
Okay, take a second. Maybe even pause and just soak this in. This table is everything we've just talked about all in one place. It links the type of structure to the particles, to the forces you have to overcome, and then to the final properties. Honestly, if you can get your head around this and even sketch it out from memory, you have absolutely nailed this topic.
So you might be thinking, okay, great for my exam, but why does this actually matter in the real world? Well, this quote from the AQA specification says it all. This isn't just some abstract theory. This knowledge lets scientists and engineers actually design new materials with exactly the properties they want, whether it's super strong alloys for jet engines or new plastics for medicine.
And that's where we're going to leave it. This stuff isn't just about explaining the world. It's about being able to change it. So think about it. If you were the one in charge, if you could build a material from the atoms up, what would you make? What job would it do? And what kind of bonding and structure would you give it? Something to think about. Good luck with the revision.